Okay, looks like we're working. So we're going to talk about minerals today. And minerals are they're a beautiful thing. Some of them are precious, some of them are just, pretty common. They're what make up rocks for the most part. So they're important to us in terms of identifying different rocks and what they are, but they're also important because, well, they're beautiful. They're gemstones come from minerals, right? So it's kind of fun to find these things. This is a cave. This is one of the largest crystal cave systems that there are, like, in the world. This is down in New Mexico, or Mexico, I think. It's Cave of Crystals, and these are gypsum crystals, which is actually a neat mineral. It's the same mineral that's in your wallboard. Has anybody ever accidentally punched a hole through their drywall? No? Never happened? No? Okay, don't do it. It's not good, right? But yeah, if you accidentally put a hand through a drywall, you'll notice that it's very white and kind of dusty in there. That's the mineral gypsum. And in its crystal form, it looks like this. It's beautiful. I mean, these things are amazing. You're not going to find crystals like this in Indiana. But we do have gypsum mines in Indiana. So it's a very soft mineral. It's really beautiful. It comes in lots of different shapes. So some minerals are very specific as to their shapes. Other minerals have multiple shapes that they could occur in. Crystal habits, we call them. I'm going to show you guys some of these as we go. So this one I'm going to walk around with because I don't want it to get dropped. This is known as a selenite rose. Isn't that pretty? It's super fragile. This is the same as the crystals you're seeing up there on the screen. It's a different way that it's grown. So both of these are gypsum. This is just called selenite rose. It looks like a rose, doesn't it? It's really cool looking. I mean, if I drop it, it'll just shatter, but it's really pretty. Yeah, you can touch it. It just kind of, it's neat, isn't it? So they occur in different shapes, but the shapes are specific to the minerals. So we'll look at that a little bit here in a minute as we go. And like I said, minerals are important to humans for lots of reasons. We've discovered more than 4,000 of them on the surface of our Earth. And there's probably many more combinations in which elements could bind together to form the compounds that give us minerals. These are what build rocks. So sometimes identifying a rock boils down to, can you determine what minerals are in it? What's its mineralogy? So we'll utilize some of these minerals. The rock-forming minerals, there's really not that many of them. But all the really neat, pretty minerals, there's lots and lots of those. So most minerals are kind of rarish compared to a few that are really, really common. And of course, we're interested in minerals. We use this stuff for everything. Everything from our computers to a lot of our modern life. Now, the characteristics of a mineral, we mentioned this before, we talked about it in class, but let's just refresh it. They have to be inorganic. In other words, not come from living things. So bananas are out, right? And for lots of reasons, probably. They've got to occur naturally. So things like bricks, and for other reasons, aren't going to be able to be considered a mineral, right? How about something like this cubic zirconium? Does anybody have a cubic zirconium ring or earrings? No? Do you know what cubic zirconium is? It's a fake diamond. It's basically diamond, but it's man-made. So that means that it can't be considered a mineral, even though it essentially, in every other characteristic, it's a mineral. They've got to be a crystalline solid, so they are crystal-like. They won't always look like a crystal, but there's an orderly arrangement of atoms. The atoms are all bonded together in sort of a crystal lattice that has a specific structure that repeats through the whole thing, which is also what gives them the shape that they have. They need consistent chemical composition. So while this rock on the far right over here, which is diorite, has multiple minerals in it, these white ones and these black ones. As together, it's a mixture, it's a rock. So it's made up of minerals, but it's a rock. The glass over here doesn't fit the bill because it's not a crystalline solid. We're going to talk about that in a second. I know it looks kind of crystally, and sometimes we call crystal glass or glass crystal, but it's not really a solid. So we'll look at that here in a bit. Actually, right now. So the atoms in a mineral, if we were to look at them, there's little balls here, they're in a regularly repeating structured pattern. Do you see the ones up top here? They're all kind of amorphous. They're all over the place. This is the reason that something like obsidian, which I brought a piece of out here. We already looked at this. This is actually a rock. Obsidian, if it weren't for this characteristic, this would be a mineral. It's silicon and it's oxygen, and that's the only thing in it. Okay, and it looks very pure. I mean, it looks like a crystal almost. But this is technically a glass. Its atoms look like that, not like this, which gives it some unique characteristics. One I'm going to demonstrate for you here, if I can do it carefully. Put my goggles on. Just grabbed a piece of basalt. We'll use this bucket here. I wish I had a trash can. I don't see one. Well, I'll try not to make a mess. So this is what the Native Americans, of course, made a lot of their arrowheads out of. And we mentioned this before. Let's see if I can do this carefully and not mess myself up. There we go. Hard to do over a bucket. I'm throwing some flakes off the, there we go. There's a nice one, do you hear it? Throwing some flakes off the obsidian and trying to make an edge here that's sharp. Now I have to dull this back down before we put it back in the mineral drawer because somebody will cut their hand on it. But if I can get a piece to come off of here. There we go. That's a pretty good edge right there. This stuff will break to the molecular level. It will be 1 molecule thick where it's broken. That's as thin as you can get. It's so thin they used to use this for eye surgery because instead of cutting through cells, it just spread them apart. So it heals really fast. But boy, will it cut the heck out of your hand if you mess up with it. It will just slice you wide open. So if I put a piece on this paper here, I don't know if I have a sharp enough edge that I've cut. I could do this with a piece of leather, or if I was skinning a deer, I would just literally slice the deer wide open. I can't find the edge. I don't think I got it. Still don't have a piece that's cut. You can hear them coming off of there. Those are conchoidal fractures, by the way. So it breaks this little cup out. I think we mentioned that in class before. Come on, find an edge. Cut myself. There you go, hold an edge of that for me. We'll kind of hold it tight. Hold up by the top. Oh, grab that piece. I'm destroying my paper. I can just find the sharp edge that I split. Well, this might be a demo for another day when I have a bigger piece of obsidian. Let's try that piece that I split off there. It's kind of, see how thin that edge is? You can almost see through it. Try that a little bit there. There we go. Oh. It is sharp. It's super easy to just, cut your hands when you're flint knapping, when you're making. But you could imagine how quick it is to skin a deer like this. You can just rip it right open. But as soon as you hit a bone, the edge of this is real brittle and it shatters. So you have to keep sharpening it, like I was just doing. But that's essentially how arrowheads are made. But that's a rock. Otherwise, it would be a mineral if it wasn't for the fact that it doesn't have an orderly crystal structure. All right, I'll keep going here. We're going to go through a lot of properties. So we mentioned the crystal lattice, this structured crystal sort of pattern. If we look at it, a lot of crystals, their internal crystal structure is reflected in their internal mineral or chemical structure is reflected in their external structure. This is actually a diagram over here, the sulfur and lead of galena, which is a mineral that has all these big lead atoms interspersed with sulfur atoms. And if you smell it, it actually smells a little bit sulfury. I happen to have a piece of galena over here. And if I had a nice piece that was still crystalline, I'll try and find one that's got some crystals on it. So these are all broken. If I have a crystal piece. But this would be a piece of galena. You see, it even looks metallic. Okay. I'll let you guys see this one. Trying to pick these off because they pull off very easily. But this is pyrite. This is the actual mineral, how it formed in these perfect little cubes. You can check it out if you like. They're absolutely perfect. Somebody tore some of them off of there. But that's the mineral pyrite, otherwise known as fool's gold. Sure looks like gold, doesn't it? But it forms perfect cubes as crystals. If you look inside of it, its atoms are really similar to this, arranged just like that. So looking at crystals, we can actually look at the angles of the crystal. In that pyrite I just showed you, they're all 90 degrees. Every single angle on that thing is 90, and it makes a perfect cube. In terms of some crystals, all of the angles, even though they might be different sizes, like different widths, the sides might be different widths, the angle will always be the same. Here's quartz. Quartz will always have a 120-degree angle between every crystal face around the rim of it here, not up top where the point is, but we can demo this. I have here a goniometer today, if I can find it. There we go. Here is a very large quartz crystal that a friend of mine picked up out in California. And here's a goniometer. It's just a way to measure angles. You put it on one angle, B there, and you turn it over to the other angle, and then where it lines up there, whoop, come on, should give us, if I get it on there straight, 120 degrees where the little line goes. So you can try this for yourself, but what's more, and you can check out that quartz because it's really cool. So a big hunk of quartz. I can take another piece of quartz, if I can find one. A lot of minerals laying around here. There we go. Here is a much smaller piece of quartz with a crystal, and the angles will be the same on this too. So go between A and B. These angles will be different, but those are the same. So you should hit 120. Even on this little one here, you should hit 120 every single one all the way around. Should not matter. So if I see 120-degree angles in a mineral that's as hard as that, I'm almost assured it's quartz, even if the sides are a little bit different lengths. So sometimes the angles of the crystals can be helpful. Some of you guys noticed out at the creek, I was like, I think that's calcite. I'm almost sure it is, because I saw one angle. The rest of it was rounded, and I could see one angle of the crystal, and I knew it was calcite. Okay. The bonds that happen in minerals are pretty important. Okay. They help show us the mineral properties as well. Like in terms of some of these cubic crystals, their internal structure, and this is salt up here, sodium chloride, it makes neat little cubes like this. So when you look at a structure like this, you can actually determine somewhat what it might look like on the inside. Now there's three types of bonds that we look at. There's ionic bonds, covalent bonds, and metallic bonds. And it doesn't really matter, we're not getting too much into the chemistry of all this, but ionic bonds tend to be a bit weaker. Okay, that's the stealing, where they're stealing electrons. So things like salt, which are ionically bonded, you can throw it in water and it'll dissolve. So there's some minerals that will dissolve in water. Other minerals are covalently bonded, like diamonds, and those bonds are really hard to break. They're held together very tightly. They're not going to dissolve in water. And then there's metallic bonds, which you can see in that pyrite. So that's a type of covalent bond where the electrons are free to flow along the surface. So that gives it that funny, shimmery, metallic look. The electrons are actually moving along the surface of that thing. In many metallic things, you can hook electricity up to, right? And electricity will flow through them. So we'll see some of that as we go through some of these. Here's that picture of salt. So the internal form the external forms depend on the internal composition. And as we break salt, salt will continue to break into tinier and tinier pieces that are all cubes. So we're going to try that out. You guys have some microscopes. Flip one of those on. You should have a little petri dish with some salt in it. go ahead and put that under the microscope. There's some petri dishes back there, you guys can grab one. Put it on the scope, turn the light on, get the light from the top, probably not the bottom. Focus that in, look at some of that salt. If you've never seen salt under the microscope, it is pretty neat. You should see a bunch of little cubes. Then after you've looked at it, take your thumbnail and crush a little bit. And see with the microscope if you can actually see that it crushes down into tiny little cubes. It should just keep making cubes. Now sometimes they won't look cubic because they'll be like jagged, they'll be like steps. They'll go down like little stairs because they break little pieces out. They're over there on the physics tables, guys, if you grab one of the stereoscopes. Up here, we're going to talk about a few other of the characteristics. So you might have heard before that a diamond is just a bunch of carbon, and it is. It's a bunch of carbon bonded together, but the differences in the bonds between a diamond carbon and that of, say, graphite, which is what's in your pencil, are vastly different, okay? The carbon atoms are held together differently. In the diamond, which is over there on the left, look at the way it's arranged. It has these strong covalent bonds. It is the hardest mineral that we have. The diamond will scratch everything else. It's our hardest mineral. The way its bonds are arranged and the fact that they're covalent makes it so strong. In terms of graphite, graphite's actually bonded together in sheets where the sheet is a sturdy bond, but the bonds between the sheets are really weak. So when you write with a graphite pencil, you're actually rubbing off little flat sheets of it are coming off. So you could probably do that under the microscope. If you just kind of rubbed off a piece on a piece of paper, you'd see little flecks of it. It doesn't come off in like how you think it might come off. Little flat pieces are coming off of it. But it's got really weak bonds between it. Still, it's just all carbon, right? Depending on how it's bonded together. We call that a polymorph. So when crystals start to grow, it's actually really neat. You need certain conditions to grow a crystal. A lot of our crystals in Indiana form inside of geodes. So if you bust open one of those rocks and you see inside, there's all sorts of crystals. So you need a cavity, something they can grow in. And then there has to be some sort of solution of liquid that contains the minerals or the elements that you're going to precipitate into that. So think about a liquidy solution here in all of these little atoms, little ions, attaching on and building this mineral and it growing outwards. And they'll grow outwards until they run into another mineral. So this mineral might keep its beautiful shape right up until it hits the side. So some geodes that you bust open, it's like the crystals just all throughout the whole thing. It doesn't look very good. But other ones are hollow, and you see like perfect crystals in there. Yeah, John? Absolutely. We can totally do man-made growing crystal. We can make all kinds of crystals in the lab. Some of the best crystals that have ever been made have been made in space, where gravity doesn't screw up their growth. Because even the gravitational force on it can help keep it not growing perfectly. So if we want perfect crystals, space is probably our best bet. But let's try and grow a few here. Okay, so looking at crystal growth, those crystals grow, like I said, essentially until they meet a surface that deforms them. So they'll grow kind of perfectly in a euhedral shape until they run into something. So there's a lot of ways you can form a crystal. They can form from a liquid, a supersaturated solution like I just did for you there. They could form from molten rock. Like liquid rock, it's going to crystallize. And as it crystallizes, the atoms attach together specifically and make minerals. Right? If those minerals form in different spots and then all harden together, you've got a rock with different minerals in it. It can form from freezing. In fact, ice is a mineral. So when you eat ice, you're eating a mineral. Same thing as when you eat salt, you're eating a mineral. As long as it's not human-made. So precipitating from a solution, evaporation is another pretty common way. You see this, if we put a bunch of salt in water and evaporated it, it would eventually, it would all crystallize as the water left the salt behind. That's a pretty common way for things to form. And then there's some weird ones like solid state diffusion. Garnets, we'll look at garnets. They're beautiful, semi-precious stones. They form through metamorphism. So when the rocks get heated and cooked a bit, the minerals will form inside the rocks and migrate through them. It's real neat. Biomineralization, when a clam makes its shell, you guys found some of those shells down at the creek. That's biomineralization. The clam is taking the minerals or the elements out of the water, the calcium, the carbon, out of the water, combining it together to make the shell. So a pearl, in a way, is kind of like a, I don't know, a mineral made by a living creature, right? Just as our bones are a mineral we make. Like we make a mineralized skeleton. It brings it home when you think about it like that, right? So let's start to look at some properties, because this is what you're going to want to know for today. On your papers, you're going to be filling some of these out. Some are more diagnostic than others. Here's an example. Pyrite, which I just showed you over there. If you see nice crystals on it, they're going to be perfect little cubes, like perfect. And that's kind of a dead giveaway for pyrite, but we don't always see the crystals. Sometimes they grew into stuff and they don't look right, or they've been broken and they don't look right. But there's other characteristics of this as well. If you smashed it, it would smell kind of sulfury. Okay? That is fool's gold. It looks like gold, doesn't it? But its streak is not gold. If I streak that, it's going to be black. It's a dead giveaway. You know you've got pyrite. Now, you've probably heard the old stories of the miners grabbing a piece of a rock and trying to figure out if it's gold and biting it. Have you ever seen that in the cartoons or anything? So they bite it because gold is not as hard as pyrite. That's iron sulfide. If you bite iron sulfide, you're breaking a tooth, right? If you bite gold, you could potentially, a big enough piece, kind of smush it a little bit, and it would be a lot softer. An easier method would just be to rub it on something else and see what happens. But, you know, it's old-timey movies. You have to bite it and see what happens. Lose a tooth. What? Do they bite the gold medal? For real? Is it really gold? Are the medals real gold? Are they? Well, I suppose they probably should be, right? I mean, it's the Olympics. So the silver ones are really silver. The bronze ones are really bronze. I guess I never thought about that. Every medal I've ever won was fake. So, you know, participation medals, everybody gets them. Yeah, I'm not going to try and bite one of those. Okay, next characteristic is color. It's the very first thing you notice, and sometimes it's the least useful. Okay, color can be useful. I don't want to badmouth it too much, but you don't really need to know much to identify color. You look at it and go pink, clear, white, green, right? Sometimes a mineral is always one color. Malachite's always green. But other times, in the sense of quartz, you'll end up with things that are quartz, but yet, far from being the same color. This is quartz. It's perfectly clear. Like, it looks like a crystal glass. Isn't that cool? This is quartz, smoky quartz. It looks a little bit darker, a little more dingy. Let's see what else we've got in here. Rose quartz, which is what's pictured up there. We also have, get that one out, leopard jasper, which is essentially quartz. We have amethyst, which is just quartz with iron and magnesium in it, mixed into it. That's all it is. As beautiful it is, that beautiful purpley amethyst is really just quartz. Even a geode is essentially just quartz inside. Okay, so they would all be the same hardness, but it can look very, very different. Here's another one. This one's striking. Calcite, which you guys found down at the creek. Some of you did. It looks very yellowy. You might have had here's another quartz. That's quartz. Yeah, right? It almost looks like your calcite. Calcite might look like this. Look at the angles on this. Those weren't cut. That's natural. Okay. Calcite might look like, this. Green. Calcite might look like this. Blue. Those angles are the way that it naturally is. This is a perfectly grown crystal. Do I have any other calcites in here? I think that's it for my calcites. But yeah, lots of colors. Calcite can be clear, calcite can be white, all sorts of colors. So it's not always most useful to look at color, but you should, right? Now, something that goes along with color, but is very useful in combination with it, is streak. We're going to rub our minerals on these little streak plates, and the powdered form of the mineral, make sure you get this, the powdered form of the mineral is what streak is. You might see that on a question. It's the powdered form of the mineral, and it doesn't have to be the same color as the mineral. And when it's not, it's like a dead giveaway. Like in the case of pyrite, pyrite's gold. But if you rub it on a streak plate, it's black. Couldn't be more surprising. There's hematite, which can be black and other colors, but if you rub it on a streak plate, you get a rusty brown. So it's like a dead giveaway. So streak is a really useful thing when the streak is different than the color of the mineral. Okay, it can really help you figure it out. So we'll use those streak plates. It's just an unglazed porcelain. Luster is another thing we're going to put down today. And I'll give you some words to go off of. Here are some lusters. You're welcome to kind of jot those on your paper so you know. The first thing you might notice is it metallic or non-metallic? So metallic would be like that pyrite that I just had. This fool's gold, it's super metallic. I mean, it looks like metal. It's shiny like metal. Non-metallic lusters would be like vitreous, which is glassy. So here's the quartz. Quartz is very glassy. I mean, even the clear stuff looks like glass. Right? So that's something you can use. Silky. Gypsum sometimes is said to have a satiny or silky luster to it. Resinous. Pearly. Does it look like a pearl? Black pearl counts too. Is it earthy and dull? Or is it adamantine? Is it brilliant like a diamond? Is it just brilliantly reflecting the light? So here's the key. Luster is how it reflects light. Color is what color it is. That's the difference. See how they're two different things? Luster can be really useful. It's the way it actually reflects the light. You're going to identify those today. Okay. What should I have? It is possible for things to have more than one luster. Something could be, depending on which type of it you have, earthy and dull or metallic, depending on which one you have. So be careful when you're looking at the characteristics today, because just because you don't have all of them doesn't make it not that mineral. Does that kind of make sense? All right, let's do the hard one. Hardness. Haha, see what I did there? Yeah. So hardness is difficult for people to wrap their heads around. It's a really simple thing when you get used to it. There's a scale called the Mohs hardness scale, and it's logarithmic, but it goes like this. It starts with gypsum, or talc is the softest mineral. Gypsum all the way on up through diamond, which is like off the charts. So diamond is some really hard stuff. So these are our index minerals, but you're not going to have a mineral test kit. You can buy them, they're expensive. So these are our index minerals. Here's what you will have, or should anyway, a fingernail. Your fingernails are about 2.5 on the hardness scale. A copper penny, which is about 3.5. A glass or a piece of steel, glass and steel are about 5.5. A hard steel file would be about 6.5. We won't have one of those. Okay. Quartz itself is a number 7. You can find a piece of quartz almost anywhere in nature, so that's why we kind of leave that up there, because a lot of time I'll pick up a piece of quartz, see if I can scratch something else with it, because I know how hard quartz is. Okay. But it all starts with your fingernail. Usually the steps are, you take your fingernail and you try to scratch it. If you can't scratch it with your fingernail, it's harder than the fingernail. For instance, if I was going to try and scratch this stuff with my fingernail, I wouldn't scratch and sniff style on it. I've got to put my fingernail on there and push hard and drag it back and forth across it in that kind of a pattern. This is not going to do anything. You might chip some off. That's not the same thing as scratching. I can't scratch that with my fingernail. It's just running across there. If anything, I'm rubbing my fingernail off. You'll tell if you're scratching with your fingernail. The penny. On the penny, pennies are round. Don't use the roundest part of the penny. You've got to kind of tip it at an angle and catch the edge and really grind it in there to see if you can scratch with the penny. So let's say that your fingernail won't scratch it, but the penny will. How hard is it? About a 3, okay? Now on the papers today, don't just write down 3. I would write down 2.5 to 3.5. Okay, see, because it's going to be a range. I'll give you the actual numbers in the lab, but if you write down 3 and it's really 2.7, you might not be able to figure it out. See? Yeah, John.
What if things are almost identical in hardness?
If like my fingernail versus what I'm scratching, usually you'll be able to scratch it a little bit, but you can kind of tell, you're like, was hard to do, but I was able to scratch it. So they could be like, you could have something that's actually 2.5 and still scratch it with your fingernail. And these are variable a little bit. Depending on the piece you get, it may not behave perfectly. That's why you need more than one characteristic to make an ID.
So can you scratch glass steel?
Yes. Well, some steel will scratch glass. Some steel is about the same hardness as glass. They're real close right in there. So on the glass part, you're going to have these little glass pieces like this, and you're going to be scratching these with your minerals. Let's say I want to find out if quartz is harder than glass. Okay? Do not hold this in your hand while you scratch it. If it breaks, it's going into your hand, right? Set it on the table and don't go like back and forth and ruin the whole piece of glass, because we have to buy these. Find a sharp corner. If it's rounded, it's not going to do anything. Find a sharp corner, put it on the glass. Ready? And look at that beautiful scratch. Glass is indeed a 7 on the scale, much harder than glass. Okay? You'll tell if it's not harder than glass, you'll try to scratch it. Okay? And I can push. You might rub some mineral off. See, I rubbed some mineral off on it, but I didn't scratch it. That's just the mineral I rubbed off on it. See that? It's not harder than the glass. And occasionally you might find a little hard chunk in there, so be careful. Like you know, play with it a little bit and make sure you know what you're doing and kind of be somewhat sure of it. But I always start from the bottom up. I always start with my thumbnail, then I go to the penny, then I go to the steel or the glass, and I kind of go up. So I've got that key for you on here, okay? So on your key for your lab, I put the steel nail at about 4.5. So see if you can scratch it with the nail. And the glass just a little bit harder at a 5.5. So you're doing the reverse. You're not using the glass to scratch it, using the mineral to scratch the glass. So be careful with your results there. A streak plate is about as hard as quartz. I didn't put that on here, but a streak plate's about a 7. So if you can't make a streak, it's about as hard as the streak plate. It's a 7 or more. So with a diamond, you just grind a hole through the streak plate. With quartz, usually, unless you're just busting it, you're not going to get anything off. It's just going to be like rubbing tile on tile. Okay? So that'll help you guys out in the lab. Let's do the next one here. Effervescence. So, some minerals will fizz. I guess I don't have any acid back here, but we'll get some. All you need is a little drop, a little drip. And if you see fizz, it effervesces. And immediately you know what you've got. And for instance, calcite, you'll drip a drip on there and it will fizz. So you'll know. So you can do that on every mineral you've got today. It's not going to hurt you to get it on your hands. Don't stick it in your eyeballs. Don't get it on your clothes or you'll have some stains. Okay? Drinking is probably not a good plan either, I would say. It's very weak acid. I mean, it's like vinegar, weak acid. So, but don't drink it, please. All right, a couple more before we get started here. Specific gravity. The heft of a mineral makes a difference. If you pick it up and you're like, my gosh, that's heavy, it's probably got some lead in it. Lead is heavy stuff. So feel it. If you pick it up, you're like, oh, that's really light. That's telling. It's a characteristic that you'll notice. The atoms are bonded together so tightly that it's very, very dense. Or they're also heavy. Lead is a heavy element, and the way that they're bonded together, there's not a lot of space in between. So yeah, it makes it pretty heavy. It makes it dense would be the correct term. And we will do density, just not today. The shapes of the crystals, we already saw some of those. We've got things, everything from rhombohedrons to cubes. Some of these you're not going to notice. You might notice these hexagonal prisms. You'll definitely notice cubes. If you see cubes, write down cubes, because boy, that'd be helpful. The shape of the crystal is a really helpful, useful characteristic. If it's been rounded in the creek, you may not have that. Or if it grew in a geode and the crystals ended up running into each other, you won't get to see the crystal structure very well. You might be able to make it out if you're careful, but it can be difficult. Okay. All right, let's talk cleavage and fracture. So, yes, geology has some of the strangest words, I know. We have rocks called schist and gneiss and all kinds of things. We also have a property called cleavage, where minerals will break along planes where the atoms are bonded together weakly. Snicker, snicker. So, how do you tell if it's a crystal face or if it's a break and it broke along the cleavage plane? It can be difficult, okay? And I'll help you with this. For instance, the salt that we were just playing with cleaves perfectly in just about every direction, right? You smash it and it makes these perfect little step marks. It breaks down. It's not that you can't break it and fracture it badly, but it usually breaks along those perfect planes. Other minerals will literally peel off in sheets because they break along a perfect plane. If you smack it with another rock and it shatters like happened with the obsidian, that's a fracture. It just like cracked through. It didn't break along nice, neat planes. So all we're going to write down in our lab is, does it have cleavage or is it fracture? That's the only real question we're not going to try and count how many planes or which directions. That gets way too complicated. Just did it break nice or did it not break nice? Here's some directions that things cleave. A mica will peel off. You can like slide a knife between it and peel off sheets. Feldspar will make these nice 90-degree angles, right? Amphibole will make these weird 60-degree angle things, but they won't be at 90 degrees. So all those things can be helpful to figuring out what mineral it is. Here's one. There's the salt you guys were just playing with. The mineral salt is actually called halite, and I happen to have some halite here. I'll let you guys sample it. Oop, fire that back up. We talked fracture, and this is a specific type of fracture known as a conchoidal fracture. When obsidian breaks, like I was doing, it breaks in these funny little scoop-like, glass-like fracture patterns, just how glass would break. Quartz will do the same thing sometimes, and quartz is a mineral. Okay. So that's obsidian. What does it look on the inside? I know we kind of mentioned this already. Obsidian is not a mineral because it's an amorphous solid, like glass is. All of the atoms are like kind of all jumbled up in there. It's not that it isn't really solid, it's just that they're all jumbled up. See the crystalline structure of quartz? It's in these nice repeating patterns. And that's what causes it to break the way that it does and why we don't consider it a mineral. But we won't get too much into that. Yep, we just tasted some stuff. It was good, right? Let's look at another fun property called transparency and double refraction. Turns out some minerals are so clear you can see right through them. Along with taste, we also have smell. Every so often you've got to smell your minerals, see what they smell like. Creek water most of the time. But some of them will actually smell, and usually sulfur is what we're smelling. So this one that looks like fool's gold, if you get some acid on that and you smell it, you will probably smell the sulfur in it. And sulfur itself is a mineral, so if you found some really yellow stuff and smelled it and were like, that's rotten eggs, it's probably sulfur. Okay. And then lastly, magnetism. We will test magnetism of all of our mineral samples today to see if any are magnetic. All right. So let's look at what we're going to do in our lab. If we take a look at our labs here, flip that back over. We're going to try, I don't know how much time we have left here. I do, don't I? There we go. Good deal. You're assuming that I remember when the mods start and end. So I've got 9 minerals set out here, and you guys are going to go through and you're going to write down the color, the streak, the luster, the hardness, if it fractures or cleaves, okay, does it break nice or not break nice? Leave density out. We're doing that another day. And if you notice some other properties, does it fizz? Can you see through it? Okay, is it magnetic? Those are other properties. Do you see little cubes? Those are the other properties. The name, let's hold off on that because we need to go through the rest of the lab first, okay? So all of those are listed in here in your lab. So you'll be able to see them. Let me give you, if you're like wondering about lusters, you can look through here, like glassy, metallic, glistening, resinous, waxy. Those are the types of lusters you're going to be using, okay? So, and for cleavage, you can just write cleavage or fracture, whether it does or not. I would suggest start with one mineral, do everything for one mineral, then get the next one. Some look really similar, so be careful you grab the right one out of the box. Your hardness set is down here, so you know where it's at. Okay? All right, we'll get started with that.